We're looking at the Taylor series and polynomial multiple choice review. Number one, let the Taylor polynomial represented by this equation here. This is a fifth degree Taylor polynomial for the function of f about x equals 0. What is the value of the third derivative evaluated at 0? So we can just go through and find the third derivative and then plug 0 in. So f prime is 6x minus 15x squared. And then actually there are more terms here, but we left them out because we know that by the time we get to the third derivative, these terms will still have x's in them, and when we plug 0 into them, it'll just drop out. So next derivative, so second derivative, 6x becomes 6, 15x squared becomes negative 30x, and then the third derivative, the 6 drops out, leaving us with just negative 30. And then the other terms here still have x's attached to them, two derivatives down. So when they get plugged in for 0, then the only term left is negative 30. Okay, number 2, for what integer k, where k is greater than 1, will both these rule of sequences converge? So we're given the choices between 2 and 6. Let's start off with something a little bit easier. This is in the form of a geometric series. So we know that geometric series will converge for any value that where the ratio is less than 1. Okay, so the only values that will cause this ratio to be less than 1 is if k is 2 or 3. Anything from 4 greater, we know the series will not converge because the geometric series with the ratio would not be less than 1. So we can cross out 4, 5, and 6. We're only down to 2 and 3 that we have to choose from, because 2 and 3 both work for k over 4 to the n. So now we've got to decide which one of these two will fit better, will cause this first rule of sequence to converge. So let's test 2 first. If we plug 2 in, negative 1 to the 2n, the same thing as negative, it's just the same thing as 1 to the n, because that 2n will cause every term to be positive. So it's really just 1 over n. And if we think about 1 over n, that's going to be a divergent harmonic series, p series of a p greater p is equal to 1. So we know that 2 is not going to cause this rule of sequence to converge. So, but if we plug in 3 in for k, then it becomes negative 1 to the 3n over n, and then we know that this series will continue to go back and forth between positive, it will alternate between positive and negative values. So now we have a alternating harmonic series, which we know will converge by the alternating series test. So therefore answer is 3. Okay, number 3, Taylor series for natural log of x is provided by this here. Okay, and let f be the function given by the sum of the first 3 non-zero terms of the series. So if we think about natural log of x, we can build natural log of x centered at 1. So we can just plug 1 in first, then plug in 2, then plug in 3, and that will produce our polynomial, Taylor polynomial, which is just an approximation. So we have the approximation provided by f of x, and then we have the original function, which is natural log of x. So it says the maximum value of the absolute value of natural log of x minus f of x for x between 0.3 and 1.7 is which of the following. So we're trying to figure out which of these, what values between 0.3 and 1.7 will cause there to be the largest difference between the original function and the polynomial. Okay, so if we think about the endpoints here, 0.3 and 1.7, we actually only need to test 0.3 and 1.7. And the reason being is because this natural log function, right, if we find the second derivative, negative 1 over x squared, the graph is actually going to be concave up from the endpoint to the other endpoint. Okay, so we'll always be concave up through those points. And if it's concave up, then that means the endpoints will have to be, one of these two will be the maximum values. Okay, so now if we plug in natural log of 0.3 minus f of 0.3 versus natural log 1.7 minus natural log 1.7, if we plug this in, we just have to compare which of the 2 will create the larger value, and at 0.3 the larger value will be 1.45 will be greater than 0.038. Okay, second page. Number 4, what are the values where the series will converge? Okay, so we know there's two main options here, either between -3 and -1 or between -1 and 1. Okay, and let's test out -1 and 1 first. So if I plug -1 in, -1 plus 2 will be 1 to the n over square root of n. So 1 over square root of n essentially is 1 over square root of n. And if we think about this in terms of p-series, this is essentially p-series of 1 over n to the 1/2. And if we see a p-value that is less than 1, we know the series will not converge. So -1 is not going to work. If I plug in 1, I get 3 to the n over root n. And this is the same thing where essentially we know that since -1 doesn't work, if we plug in 1, we're getting the same issue where we have p-series of value that is less than 1. So therefore, we know that D and E will both fail due to p-series telling us that the series is going to diverge. So now we're down to these three options, okay, between -3 and -1. So let's just test -3 and -1, because really it's the endpoints that's the difference between each of these options here. So let's test -3 in. If I plug -3 in for x, -3 plus 2 was -1 to the n. So -1 to the n over square root of n. Now this normally would not, if it were an alternating series, this would diverge by a p-series test. However, because this is alternating, the restrictions for converging series is going to be a little bit more relaxed here. The rules will be a little more relaxed because all that needs to happen for the 1 over root n is that it just needs to go to 0. So the limit of the positive form of 1 over square root of n, it does go to 0. So that's enough to for this alternating series to converge. Now let's look at what happens with -1. If we plug -1 in, -1 plus 2 is going to be 1 to the n over square root of n, and we know that p-series will cause that to fail. So we know that -1 cannot be the option, but let's just make sure that something like -1.1, okay, will work, because we know -1.1 falls between -3 and -1. So if we test out -1.1, -1.1 plus 2 to the n, okay, plug in -1.1 in for x, and if we combine that, we get 0.9 to the n over square root of n. Now this may not be apparent as to whether this converges or not, but if we pull out, if we make this 1 over square root of n a separate term from the 0.9 to the n, so let's think about 0.9 to the n. We know that this is going to be a converging geometric series because the ratio is less than 1. So by direct comparison, if we know that this series will converge, then we know that this divided by root n must be a smaller series, must produce a smaller value than just 0.9 to the n. So we know that by direct comparison test, because 0.9 to the n over square root of n is less than a converging series, a known converging series of 0.9 to the n, we know that this overall series will converge. Okay, so we know that -1 will not work, but if we test a value less than -1, then we know that works. So our answer choice is going to be B. Okay, number 5. The graph of the function represented by the Maclaurin series. Now we need to be able to look at this Maclaurin series and recognize that this is similar to something that we know. This is similar to the e to the x, because e to the x is 1 plus x squared. Basically, it's the positive version of this rule of sequence. So we know e to the x looks like this, right? So then how do we get from here, how do we get from e to the x to this new series? What we can do is, if we replace every x with negative x, then essentially every other term, any term with a negative odd exponent, will cause the alternating term, or every other term, to be negative. So really, we know that this is referring to the rule of sequence for e to the negative x. So essentially, we're asking, when is e to the negative x going to intersect the graph of y equals x cubed? So we can just graph these two equations and then look for the intersection. Another way to do this is we can write this as one equation, do x cubed minus e to the negative x, and just look for the x-intercept. Okay, so that could be a little bit easier to identify a point rather than having to search all over all four quadrants to figure out where these intersect. If we just do x cubed minus e to the x, then we can just limit ourselves to looking at an x-intercept. And the x-intercept is 0.773, so that's where the two graphs will intersect. All right, which of the following sequences converge? Gotta be careful here. This is not asking where the series will converge, it's asking when the sequence converges. So all it takes for a sequence to converge is, as long as the limit of the rule of sequence as n approaches infinity, as long as it approaches a real number, then that is enough for the sequence to converge. So let's just evaluate the limit of each of these rule of sequences. So limit of 5n over 2n minus 1 as n approaches infinity, we see that the degrees match, so we just take the leading coefficients, so 5 over 2. Okay, so we know that this first sequence, converges to 5 over 2. E to the n over n, so e to the n over n, we're looking at a exponential function over an algebraic. So we know exponential will grow at a faster rate than the algebraic. So we know that this series will diverge to infinity. Okay, third one, e to the n over 1 plus e to the n. Think of these as like degrees. So the highest degree is with this exponential function. And because they are the same, we just look at the leading coefficients. So 1 over 1 is equal to 1. So we know that this rule of sequence will converge to 1. So therefore, only the first and third sequence will converge. So answer choice D.